Hi everyone, today we're going to be talking about topic 4.7, the types of chemical reactions. We're thinking of the types of basic chemical reactions. There are really 5 major reaction classes that we are mostly going to be concerned about in AP Chem. The first is known as composition, also sometimes referred to as synthesis. In this reaction, you have A plus B goes to AB, right? You have 2 components mixed together, make something new. So for an example, we have sodium solid plus chlorine gas reacting together to form sodium chloride, right? And of course, if we want to balance this would be 2 and 2, right? And this is a solid, right? And so this is a composition reaction. You mix together 2 substances, you get 1 substance at the end. The second major class is decomposition. You might imagine if composition is putting 2 things together, decomposition is the exact opposite. So it's AB breaking apart to form A plus B. One example of this is, for example, potassium chlorate, KClO3, breaking apart. This would be a solid, breaking itself apart or decomposing to make KCl, which is a solid, plus O2 gas. And if you want to balance this, of course, we should have 3 O2, we should have 2 KCl and 2 KClO3, right? Because we'll have 2 potassiums, 2 chlorides, and 6 oxygens at the end. Another common examples that we'll see is the decomposition of hydrogen peroxide, so H2O2, liquid, decomposing to make H2O, liquid, and O2, gas. If you want to balance this, we would do 2 H2O2, or 2 hydrogen peroxides, and 2 waters at the end. This is a decomposition, but it's just a little bit harder to see, so I wanted to at least show it as an example. The third major class of reaction that we'll often be encountering are single ionic replacements, also sometimes known as a single displacement reaction. In this reaction, we'll have A plus BC reacting together, where BC is an ion, right? It's ionic, to make AC plus B. Now, you've seen a lot of examples of this previously. For example, if you take zinc solid plus nickel chloride, NiCl2 aqueous, right? It's ionic, and so we should have some ions somewhere. Those react together to form zinc chloride, ZnCl2 aqueous, plus solid nickel, right? And that's already balanced, so we don't have to do any balancing there. Another version of a single ionic replacement reaction is a little bit harder to see, but it's one that we're going to encounter. And that is, for example, if you have magnesium solid, right? That's our metal portion, plus hydrochloric acid, HCl, and this is aqueous. You form MgCl2, aqueous, as you might imagine, right? The Mg mixes with the Cl, but you also form H2 gas, right? You don't form H+. The hydrogen ions together form hydrogen gas. And so if you want to balance this equation, it'd be Mg solid plus 2 HCl makes MgCl2 plus H2 gas. This is a bit of a stranger single ionic replacement reaction, but I wanted to at least put it in our minds. It's something that we will see in the future. The fourth major class of reaction is the double ionic replacement, or the double displacement reaction. In this reaction, we will have AB plus CD will make AD plus CB, and C is specifically first because that is our cation. An example is lithium chloride reacting with silver nitrate. This will do a double replacement to form lithium nitrate, which is aqueous, and silver chloride, which we've seen a lot before, is a solid. The last major reaction class is a combustion reaction. And in reality, all this means is reacts with O2. So if you ever see O2, you immediately need to think a combustion reaction. So in this reaction, typically it's done with a hydrocarbon, and so CXHY, carbon bound to hydrogen, plus O2 makes CO2 plus H2O. Now, occasionally this will also be CXHYOZ, right? You can also see that, but at the very least, you need CXHY reacting with O2. So for example, we could have C3H8 plus O2. This reacts to make carbon dioxide plus water. If we want to balance this, of course, we should have 3 CO2 in order to balance off the carbons. We should have 4 H2O in order to balance off the hydrogens. On our right side, we'll have 6 oxygens plus 4 oxygens. That'll be 10, and so we should have 5 O2. The other kind of combustion is not with a hydrocarbon, but instead with a metal. And so you can have some sort of metal, X, plus O2, reacting to form XO. So an example that I can think of is magnesium, solid, plus O2 gas, reacts to make MgO, magnesium oxide, solid. And again, if you want to balance this, it should be 2 magnesium plus oxygen makes 2 MgO. Now, one really important thing with single replacement reactions is known as the single replacement activity series. This essentially tells you for a reaction to be spontaneous. Spontaneous meaning proceeds without an external force. In other words, happens once mixed. So for example, when you've seen in class when I did that precipitation of lead iodide, right? Lead iodide precipitated on its own. I didn't have to add any extra, anything extra into it. And so the solo element needs to be more reactive than the ion of the compound. So for example, if we look back to that reaction of that I showed with the single ionic replacement, Mg plus HCl reacts to form MgCl2 plus H2 gas. In this particular reaction, and this should be 2HCl, in this particular reaction, if we look at our table, we should see that hydrogen is all the way down here, and magnesium, Mg, is all the way up here. This is increasing reactivity. And since magnesium is higher than hydrogen, this reaction happens without any external force. I can mix magnesium and hydrochloric acid, and I will get magnesium chloride and H2 gas. Now, of course, those are the 5 major reaction classes of what's actually happening with the molecules, but there are certain results that can happen, or kind of alternative reaction classes that we also want to consider. One is precipitation reactions. We talked about this quite a bit, but it's when 2 soluble solutions of ions mix to form a precipitate. In other words, AB, aqueous, plus CD, aqueous, react to form AD, solid, plus CB, aqueous, right? Or it could be CB, solid, AD, aqueous. It doesn't really matter. One of them is going to be a solid, right? The example that I had shown in class was this lead iodide precipitation. We must also remember our solubility rules right down here. Sodium, potassium, ammonium, and nitrate, if you ever see those in an ionic compound, they will always be soluble in water. Otherwise, it will depend on the particular compound. Another major reaction that we're going to be talking about and really expanding upon in Unit 8 are acid-base reactions. And so acid-base reactions involve the transfer of one or more protons. Now, by protons, I don't just mean random protons. I mean specifically hydrogen cations, or H+, right? If you take an electron away from hydrogen, the only thing left is a proton. We're not actually ripping a proton off of a molecule. It's just a hydrogen that has had its electron removed to make a proton. That's what we mean by a proton. So that's what that means. An example of this would be HCl, aqueous, reacting with sodium hydroxide, aqueous, to form H2O, liquid, plus NaCl, which is also aqueous. Another example of this would be acetic acid or vinegar, right? HC2H3O2, aqueous, plus water, liquid, reacts, and this doesn't completely react, and so you end up getting both of them. You get C2H3O2 minus, aqueous, plus hydronium ion, H3O plus, aqueous. We'll be talking a lot more about this, a little bit more in our next topic, but also when we get to Unit 8, we're speaking extensively about acid-base reactions. Another term for this is a neutralization reaction. And that is because you are neutralizing an acid and a base to form a salt. And so when you mix acid and base, you form a salt of some kind. And I should also say specifically a strong acid or base. And I will talk more in the next topic about what I mean by strong acid or base. Okay, the last of the major classes or types of reactions we'll talk about are oxidation, reduction, or redox reactions. These involve the transfer of electrons between species. This is indicated by a change in oxidation number and when I mean by oxidation is that there is it means either the gain or loss of electrons. The term oxidation means you lost electrons, or the species, whatever species you're interested in, lost electrons. The term reduction means that it gained electrons. I know it sounds backwards. I will explain why oxidation is called lost and reduction is gain of electrons. The most important thing to remember is that one cannot happen without the other. If something is oxidized, something must be reduced. If something is reduced, something has to be oxidized. Okay, so on the last slide, I did just mention oxidation numbers. And so if we're going to determine the oxidation reduction reaction has occurred, we have to assign what are known as oxidation numbers for each element in a neutral compound or charged entity. And so there are a few rules for doing this, and I'll show an example on the next slide. Rule number 1. Atoms in their elemental form have an oxidation number, or an oxidation state, of 0. So an example of this is O2 gas, right? This is in its elemental form, so its oxidation number equals 0. Rule number 2 is the oxidation number of monatomic, meaning one atom, ions is the same as the charge. So an example of this is if I have Mg2 plus, its oxidation number is equal to 2. Rule number 3, nonmetals usually have negative oxidation numbers. So for example, oxygen is normally -2, but if it's in a peroxide where O is bonded to O, then it's -1. Hydrogen is usually +1. Fluoride, for example, is always -1. And then arguably the most important rule, the sum of oxidation numbers in a neutral compound is always 0. In a polyatomic ion, the sum equals the charge. And so if I have, right, nitrate, for example, the sum must equal -1, right? Because the charge of the polyatomic ion is -1. And also if we take nitrate for an example, right, we know the sum of nitrate must equal -1. We know the oxidation number of oxygen is equal to -2. So there's 3 oxygens, so there should be 3 times -2 is equal to -6. If the sum equals -1, then if you want the oxidation of nitrogen, it should be -1 is equal to 6 to -6 plus n, and so therefore n must equal +5 in this case. Generally, when we're thinking of the oxidation number, the more electronegative element takes the electrons. So oxygen is more electronegative than nitrogen, and so oxygen versus nitrogen, O has the electrons. So that one should have the negative oxidation number. So let's go ahead and figure out the oxidation state of these 2 compounds that we have reacting here. We have iodine, I2, and C6H8O6, which is also known as ascorbic acid or vitamin C. In our I2, right, because this is an element, it's an elemental form, the sum equals 0, and so the oxidation state of I is just 0. If you look here at C6H8O6, we can see that C, we have 6 times carbon plus 8 times hydrogen. Hydrogen's pretty much always in +1. Plus oxygen is pretty much always in -2 unless it's in a peroxide, in which this case it is not. So it should be 6 times -2 equals the sum of the charge, which this is neutral, so it's 0. So 6 times carbon plus 8 minus 12 equals 0. 6 times carbon minus 4 equals 0. We can add 4 to each side, right? Just do our algebra. And so the oxidation state of carbon should equal 4 over 6 or 2 over 3. Now, typically, we won't have fractions as our oxidation number, but in this case, we have 6 carbons, and so on average, its oxidation number of all of them is 2 over 3, but you could figure out the oxidation number of each of them given the structure. But in this case, we're not too worried about that. We can also do that for the products. And so if we look at 2I minus, right now, the sum equals -1. And so I's oxidation state should be -1, right? Because we only have one I there. And if we look at ascorbic acid here, right, we should have carbon times, we should have 6 times carbon plus 6 times hydrogen, which is always +1, or pretty much always +1. Then we have 6 times oxygen, which is always -2, unless it is in a peroxide. And again, the sum there is equal to 0. And so we should have 6 times carbon plus 6 minus 12 equals 0. So 6 minus 12, that's just -6. So 6 times C minus 6 equals 0. Carbon, 6 times the oxidation state of carbon should equal 6, because we just add 6 to each side. And so therefore, carbon's oxidation state here is 1. And so if we look at this, each of these reactants, we have iodine has gone from 0 to -1, and carbon has gone from 2 over 3 to +1. And so this has gained electrons. This has lost electrons. Therefore, if it gains electrons, that means my iodine was reduced. It has lost electrons. That means my carbon was oxidized. Well, we'll have a little bit more practice at thinking about oxidation numbers and how to determine those, but for now, that's all. Thanks, guys.